Good morning, students. In today's lecture, we are going to see remaining part of equivalent matrix. In previous lecture, we have seen this theorem. Any two norms on a finite dimensional vector space are equivalent, as well as we have proved these 5 statements are equivalent. Okay. V with norm and W with another norm. Actually, this here there is a printing mistake, you can say. It should be triple norm. This W is with this norm. Okay. This is a printing mistake here. Okay. So here you can see here whenever Tx is there, images. Whenever we are talking about elements in W, we are taking here this notation, this triple norm, this notation. And whenever we are talking about elements in V, we are using just this notation. Okay. So this is norm on W and this is norm on V. Okay. Already I have explained it. Okay. Now we will see the theorem. Let D be dense in M and N be complete, and F is from D to N be, you can see here, uniformly continuous, then F extends uniquely to a uniformly continuous map F from M to N. Moreover, F is an isometry, so is the extension of F. Okay. Just a minute. So what is given here? D is dense in M and N is given to be complete. Okay. D is dense and N is given to be, D is dense in M means what? That is D closure is nothing but M. And what is given extra? N is complete. Okay. Complete means every Cauchy sequence converges in N. And F is from this dense subset of M to N. And what is it is given? Uniformly continuous. It is uniformly continuous. Then we have to prove that F extends uniquely to a uniformly continuous map F from whole space M to N. Okay. So if this D is the dense subset of M, N is complete, and if F is uniformly continuous, then F can be extended to the map F, which is also uniformly continuous and whose domain will be M. Okay. Here it is from subset of M. Then we are extending it to whole space M. Okay. From the function will be from whole space M to N. Okay, so how we will prove it? Let X belongs to M. Since D is dense in M, there exists a sequence Xn in D such that Xn converges to X. So this implies Xn is Cauchy in D. And now F is uniformly continuous, so its image is also Cauchy in N, right? Now, since N is complete, F of Xn converges to some Y in N because N is complete. So let say F of Xn converges to some Y in N. Now we define a map F from M to N by F of X is equal to Y and which is nothing but limit n tends to infinity f of xn, where xn converges to x. Now first we will show this f is well defined. So let xn converges to x and yn converges to x. Then the sequence x1 y1, x2 y2 also converges, and this sequence x1 y1 x2 y2 is Cauchy in D. So this implies f of x1, f of y1, f of x2, f of y2 is also Cauchy in N. Now N is complete. Again we will use that property. This sequence will converge to some z. In particular, f of x1 converges to some z, means f of yn also converges to some z. This implies f is well defined. Now we prove f is uniformly continuous. Now since small f is uniformly continuous, by definition of uniform continuity, for every epsilon greater than 0, in particular epsilon by 3 greater than 0, there exists element in D such that row of f of x dash comma f of y dash is less than epsilon by 3 whenever distance between x dash and y dash is less than delta. Now given any x in M, there exists x dash in D such that distance between x and x dash is less than delta by 3, and row of fx dash is less than epsilon by 3. Why? Because D is dense. Okay, dense means D intersection B, that open ball is non-empty. So if x belongs to this ball, intersection of that ball and D, it implies D of x dash is less than delta by 3. Is that okay? Now this implies there exists xn in D such that D of xn x dash is less than delta. Now take two elements x and y in M with distance of xy is less than delta by 3. So this implies there exists x dash y dash in D such that D of x dash is less than delta by 3, and again which gives us row of fx comma fx dash is less than epsilon by 3. But D of y dash is also less than delta by 3. So this gives again row of fy f of y dash is also less than epsilon by 3. Now calculate D of x dash y dash by using triangle inequality, and we can use like D of x dash x plus D of y dash plus D of x xy. We can write this by using metric properties, and it will be less than delta by 3 plus delta by 3 plus delta by 3 means less than delta. Okay, so this implies row of f of x dash comma f of y dash is also less than or equal to epsilon by 3. Therefore row of fx comma capital Fy is less than or equal to row of fx comma f of x dash, again the same thing, row of f of x dash f of y dash plus row of fy comma f of y dash, and which gives us less than epsilon. Therefore row of fx comma fy is less than epsilon whenever xy is in M such that distance of xy is less than delta by 3. So this gives us f is uniformly continuous. Now it remains to prove that f is an extension of f, small f. Capital F is an extension of small f. To prove this, we will prove f restricted to D is nothing but small f. That is, f of x is equal to capital F of x is equal to small f of x for all x in D. So let x is in D. Since xn is equal to x, x converges to x, this implies f of xn converges to f of x. So limit n tends to infinity f of xn is fx, and the capital F of x is also fx for all x in D. So this gives us f restricted to D is nothing but f. Now to show uniqueness, let f comma g be two maps from M to N which are uniformly continuous on f restricted to D. Say which is nothing but my small f. Let x is in M. Then there exists a sequence in D such that xn converges to x. Now since f and g are continuous, g is also continuous. F of xn converges to f of x and g of xn converges to g of x. Now since f restricted to D is nothing but g restricted to D and xn is in D, f of xn will be equal to g of xn. So f of xn converges to capital F of x and f of xn converges to g of capital G of x. So this implies fx is nothing but gx. Is that okay? So this gives us f is nothing but g on M. F is equal to g on M. Now suppose f is an isometry. So let xy belongs to M. There exists xn, yn in D such that xn converges to x, yn converges to y. This implies distance of x and yn converges to distance of xy. But what is distance of xy? It is limit n tends to infinity distance of x and yn, which we can write as limit n tends to infinity rho of f small f of xn comma f of yn, right? Now since f of xn, small f of xn converges to capital F of x, small f of yn converges to capital F of y, rho of f of x, small f of xn comma f of yn converges to rho of capital F of x comma capital F of y. Therefore distance of xy is nothing but rho of capital F of x comma f of y. So this implies f is an isometry. So this proves capital F is extension of small f. Now the next theorem is Baire Category theorem. What it says that if Gn is a sequence of dense open subsets in R, then intersection, here it should be intersection, okay, intersection, there infinite intersection of this Gn is non-empty. Intersection n is equal to 1 to infinity, Gn is not empty. In fact, it is dense. In fact, it is dense in R. Okay. What Baire Category theorem says that if Gn is a sequence of dense open subsets in R, then their infinite intersection is non-empty and that infinite intersection of Gn is also dense in R. So how we will prove this? Let x0 belongs to R and I0 be any open interval containing x0. Now what is given? G1, G2, Gn's are dense in R. Now since G1 is dense in R, I0 intersection G1 is non-empty by definition of dense set. Okay. So let x1 belongs to this intersection, I0 intersection G1. Now since G1 is open in R, this implies I0 intersection G1 is open. So this implies there exists open interval I1 such that x1 is contained in I1 contained in I0 intersection G1. Now by shrinking I1, we may assume that diameter of I1 can be less than 1. So I1 closure is contained in I0 intersection G1. Now again G2 is dense in R. This implies I1 intersection G2 is non-empty. So let x2 belongs to that intersection. Since G2 is open, I1 intersection G2 is also open. So there exists an open interval I2 such that x2 belongs to I2 which is contained in I1 intersection G2. Again by shrinking I2, we may assume that diameter of I2 is less than half and I2 closure is contained in I1 intersection G2. Therefore, I1 closure is containing I2 closure and I2 closure is contained in I1 intersection G2. This this contain again in I0 intersection G1 intersection G2. So by repeating the same process, we get a decreasing sequence of closed and bounded intervals which are non-empty, such that ion closure is contained in I0 intersection G1 intersection G2 intersection Gn. Is that okay? Ion closure, this is the closed set contained in I0 intersection G1 intersection G2 intersection Gn. Now, by nested interval theorem, what we can say? Intersection is non-empty, right? So this infinite intersection of ion closure is non-empty and it is contained in this intersection I0 intersection I is equal to here n is equal to 1 to infinity. Here it should be n is equal to 1 to infinity intersection Gn. Now since you can this subscript here everywhere we have to change here suffix this n is equal to 1 to infinity. Okay, these are typing mistakes, you can understand this easily. Okay, now since this intersection is non-empty, this intersection is also non-empty, and this gives us intersection Gn intersects every open interval. Therefore, this infinite intersection is also dense in R. And we can say that corollary Q cannot be written as countable intersection of open subsets of R. Okay, corollary of this theorem, we can say that Q cannot be written as countable intersection of open subsets of R because of this theorem. Okay, already this sequence of functions we have explained in another video. Okay, so this completes your equivalent matrix and Baire category theorem.